Okay, if a so-called shadow is the absence of light, then why does the moon turn red during an eclipse? Well, first of all, a common misconception is always propagandized by all the global Santa ballers, including Neil deGrasse Tyson, when people try to forcibly lay over the heliocentric explanation on top of a geocentric foundation. This commits a straw man fallacy. It replaces the actual explanation, which is involving optical lensing in a refractive light field, with a fake scenario claiming that it's a shadow bar, supposedly the Earth, sliding across the moon. That distorted version is always mocked and pushed, even though it's not the claim being made by flat earthers at all. The Globies are suggesting that if the Earth is a disk floating around, casting a shadow in space, a lunar eclipse would appear as a straight line on the moon. This is a classic straw man fallacy because it assumes that the only alternative to the heliocentric explanation must behave like a literal physical obstruction because you globies are so narrow-minded and insist that the heliocentric explanation is the only outcome, but it's not. It forces people who don't understand to imagine a straight-edged shadow sweeping across the moon. But that's not actually what's happening at all. Lunar eclipse effect is produced by a refractive convergence field. In optics, it's called a caustic zone, generated by the sun's scattered light. It's called Rayleigh scattering. When the full moon intersects and interacts with this caustic region, its own light is lensed through that refractive field, because this is a lensing interaction rather than a solid shadow. The boundary that appears on the moon is actually curved and dynamic. It's not straight. The caustic field itself has three-dimensional geometry shaped by three things, which is Rayleigh scattering, the conical refraction, and thirdly, birefringence, the birefringent division of the light field. As a result of these necessary optical lensing phenomena, the visible boundary of the lensing property of the eclipse appears as a crescent arc that comes in diagonally at a specific degree of angle. It reaches totality, pauses in time, rotates 90 degrees, and then gradually changes its orientation as the refractive region passes across the moon, completely falsifying the heliocentric theory. The Earth cannot be a Santa ball, stop in time, and then pause, and then literally change direction as we observe during the lunar eclipse. What we actually see during the lunar eclipse is a curved crescent boundary that gradually rotates in orientation, approaching nearly a 90-degree shift as the eclipse progresses diagonally, accompanied by a distinct blue double band lensing effect, and ultimately transitions into the deep red color of totality. And by the way, keep that double band in mind, it's very important. Secondly, Angel of Light has already proved that there is no shadow involved during the lunar eclipse whatsoever by using long-range infrared filter camera zoomed in on the eclipse with a P900.
I have two cameras set up here, pointing at the lunar eclipse. One is a P900 full spectrum, the other one is a P1000 just normal. And as you can see, the P900 full spectrum is not seeing an eclipse, it's seeing the face of the moon. But the 1000 is seeing a shadow, or the supposed shadow. The P900 doesn't see it. So somehow full spectrum or infrared removes the so-called shadow of the moon, and you can see the moon's face. So this proves that the lunar eclipse is not a shadow at all.
Proving that all the interactions that we see happening during the lunar eclipse happens in the sky and it has nothing to do with the Earth. Now, I will call this the Birefringent Sun Caustic Lunar Eclipse, based off the work of Joe Hanvey. The Birefringent Sun Caustic Lunar Eclipse emphasizes that the black sun projects its energy up to Polaris, where it refracts back down, returns downward into a conical refraction. This conical refraction is what projects and creates the sun and the moon as focal illumination points of different light intensities of their own energy. A lunar eclipse occurs when the full moon is veiled or obscured, or as most people say, shadowed, but it's not really a shadow. It just looks like that. The sun's caustic zone causes the obstruction. This event unfolds and it requires the firmament, and it arises from the refractive energy causing these caustics when the sun and the moon are diametrically opposed at specific times. Within the caustic boundary, birefringence occurs. What birefringence means is it refers to the division of a single ethereal current into two differentiated rays of light as it passes through the firmament medium. As the black sun's energy undergoes conical refraction, it does not remain singular. Instead, it separates into dual pathways, and these paired rays interact with the manifested sun and the moon, producing a double shadow lensing effect upon the lunar surface. The black sun's energy disperses throughout the celestial dome as an ethereal field. An invisible metaphysical force generates zones of intensified and diminished coherence. And the result is a caustic region where the birefringent division becomes visibly expressed as so-called moving shadows across the moon, but they're not shadows. So the moon functions like a cathodic body, and the sun is the anodic body within a celestial circuit. The moon's surface can exhibit cathodoluminescent behavior, and the sun will exhibit anodoluminescent behavior, meaning that luminous emissions occurs when energetic particles interact with the lunar material. As streams of energetic electrons coming from the sun encounters the moon's surface, they excite the lunar material to higher energy states. This process resembles fluorescent emissions rather than incandescence. Incandescence is produced by heat and thermal vibration, whereas fluorescence results from electron excitation within the structure of a material. Because the light originates from electronic transitions rather than thermal heating. Moonlight appears comparatively cold, carrying very little infrared energy relative to the sunlight. The distinction helps explain the measured difference between sunlight and moonlight. Sunlight is typically characterized by a strong thermal component, a broad and continuous spectrum, and a significant infrared energy. Moonlight, however, by contrast, appears luminescent and comparatively subdued in infrared output, suggesting that its visible illumination will arise through processes that are different than simple thermal radiation. The moon's glow and the dramatic deep red coloration are active luminous phenomena associated with celestial electrical interactions. During a lunar eclipse, a distinct electrical condition occurs as the sun's refractive convergence field, or its caustic zone. The sun emits magnetotails. NASA will call them heliotails, but however, regardless, they are electromagnetic emissions that are connected to the solar winds, and it's part of its magnetic field. As the sun and moon are diametrically opposed relative to Earth's central magnetic north, the sun's magnetotail, composed of highly conductive ionic materials, extends into this caustic region. The moon's cathodic surface therefore enters into the magnetotail caustic zone, which is an intensified plasma environment, and the plasma density between the two bodies increases toward a critical threshold, reducing electrical resistance. The caustic zone, it functions as a concentrating geometry that amplifies energetic transfer. As resistance drops, the current increases and an increased discharge spreads across the moon's surface. The deep red coloration of the blood moon results from a spectral shift that is caused by the electrical energetic oversaturation within the caustic discharge region. The energetic electrical surge generated during the eclipse, it propagates through Earth's electromagnetic environment, particularly in the ionosphere. It's associated with electrical activity and electrical ionization, producing measurable ionospheric fluctuations, and it's associated with radio wave disturbances. The eclipse is therefore the visible result of concentrated electrical discharge mediated by the sun's magnetotail caustic zone and expressed across the moon's surface. The sun produces what's called Rayleigh's light scattering throughout the atmos. As the sun's light disperses through the atmos, it travels outward like a moving canopy, generating a conical light envelope caustic pattern. Within the far red portion of the spectrum, this configuration produces the lensing effect associated with the lunar eclipse, which ultimately gives rise to the appearance of the blood moon. As the sun's scattered light passes through this refractive region, the first observable feature is the double shadow line that moves across the face of the moon. But that's not the Earth. It's not a shadow. It's a double obscuration lensing effect. The fact that this double band becomes visible should let anybody know that the Earth is not involved in this phenomena, and the band appears differently to people all across the world depending on where you are at. Your perspective will affect this. It will change how the process takes place across the moon's surface, causing it to appear at different angle orientations depending on where you are viewing from on the flat plane. This dual band appears just before the eclipse reaches totality, where the moon briefly darkens significantly. As the alignment progresses, the refracted light within the far red spectrum becomes dominant, producing the red coloration associated with the blood moon. Strictly speaking, the term shadow is not entirely accurate. The phenomena is better described as a lensing effect, although the term shadow is commonly used because that's what everybody is just taught. Now, the rotating crescent observed during a lunar eclipse is not a straight band moving across the moon like how many globe trolls like to throw at flat earthers, but rather it's the visible intersection of a curved caustic surface with the moon's circular luminous face. Because the refractive field is shaped by conical refraction, it forms a cone-like or ringed distribution rather than a flat beam. As different portions of this curved field pass across the moon, the contact angle continuously changes, causing the crescent boundary to gradually rotate. The presence of a double leading band indicates a birefringent division within the light field, where a single energetic stream separates into two refracted paths. As these dual pathways sweep across the lunar surface, their shifting alignment further contributes to the apparent spin of the crescent angle. Additionally, the moon is viewed through the layered atmos-mediated refractive medium, which alters projection angles as the lensing zone progresses, and people in different locations will see it at different angles once again. When a curved refractive boundary moves across a circular luminous surface, rotational geometry naturally results. In simple terms, the crescent rotates because it is the moving intersection of a curved birefringent refractive field with the moon's circular light surface, not a rigid straight shadow sweeping across it. So with that being said, within this context, the moon is not a passive reflector, but it's a partner in a luminous interaction, modulating and re-emitting energy through electronic excitation. This perspective provides a conceptual basis for the moon's distinctive glow and for the unusual optical phenomena observed during the deep red coloration events and the bluish tint that is seen during a lunar eclipse totality.